Welcome everybody, this is the second unit in the second week of the Parallel Programming Concepts course in OpenHBI. My name is Peter Tröger. We discussed now that we have in parallel programming the interesting condition that parallel programming actually relates to classical concurrent programming issues. So the question for doing parallel programming in the right way is, what kind of concurrency problems do we usually have? So what can happen within our parallel software due to the fact that the parallel software expresses concurrency that may be then exploited on parallel hardware. And concurrency problems is a classical thing in computer science. So the point that we have concurrent activities and that they somehow lead to a problem is well known since the 60s, especially since we had operating system support for concurrent activities since that time. So the notion of concurrency is a traditional one, and this is also typically part of operating system curricula. But here we want to debate them again in order to make sure that you got the right kind of understanding about the problems and the tools you will face when you try to do your parallelization of a particular piece of code. Let's start with a very, very simple example for concurrent execution. We take this arbitrary program, and this program in the yellow box actually performs the following activity or this method. We have the definition of two variables that are supposed to hold string values. Then we have an echo function. This echo function reads a function result. The function is called myID, so it returns some kind of identification information. As it stores this value in the input variable, then the output variable is filled with the value of the input variable, and then we print the output variable. We now take this method or this function and create two threads, two concurrent activities in our operating system, and both activities, both tasks are supposed to run the same method, this method. The interesting question is now, if you do this concurrent execution, as it is shown on the right side in the slide, what could happen? What could be the problem? So one interesting question is, if you have two threads running on a single core, what could happen with that code? And if you have two threads running on two cores, what could happen with that code? And the first relevant notion here is that the kind of effects and problems you may face with such a concurrent execution are independent from the fact whether you run on one or two cores, because the problem lies in the notion of interleaving. Interleaving means that if you have different concurrent activities, they actually form sequences of atomic statements. We try to visualize that here with the blue and the red line of instructions. So these two lines of instructions, as in the example before, basically are a combination of sequential steps, and each of the steps is assumed to be an atomic one, which means it can run at once. Concurrent execution is now the interleaving of these two instruction streams. So in order to be able to run these two sequential programs virtually at the same time, meaning concurrently, the operating system interleaves the execution by taking some instructions from the one side and some instructions from the other side. And by this, it makes sure that all of these programs or concurrent tasks have their own progress, so that the user gets the notion that the overall system runs application in parallel. The trick here is that this kind of context switching and interleaving happens very, very fast. So when you use your ordinary Windows system or your mobile phone, you can't really see the switching part. You just see that the applications all get their progress because the processor is very fast in this kind of work. If we now take this interleaving of atomic statements and declare this as the way of doing a concurrent execution, the interesting point is that different cases, different versions of the interleaving may occur. You see this on the slide in the example. So the point here is that depending on the program, on the kind of statements you have, and the kind of interleaving, your program may actually produce different results. This is the case for the echo example we had beforehand, and this is also the case here. In both examples, the main issue with the different results is the sharing of variables. So you see this here with the shared variable x. You saw this beforehand in the echo example with the shared input and output variables. So the problem with concurrency is that in the moment where you have shared information, shared variables or shared memory or even shared operating system resources, the interleaving of execution may lead to different results. This is not predictable because the actual interleaving that happens is done by the operating system scheduler on an event-based mode. So there is no possibility for predicting how the interleaving at runtime will take place. This is a crucial problem in concurrent programming, and since parallel programs were identified as concurrent programs, we have the same problem, so we have to deal with that too. The name for this kind of effect, where the interleaving of different sequential programs may lead to different results, is something that we call a race condition. Race condition is a property of the code, so you look on the code and you may or may not be able to see that there is potential for such a race condition. And this is always a bad thing, because code that does not have a clear and non-obvious way of working is actually bad code. So what you want from your software is that it behaves in a predictable manner and that you don't have to reason about how this code is run on different kinds of hardware. This well-known issue of a race condition can be treated as a generic problem regardless of the programming language, regardless of the actual approach of dealing with concurrency and parallelism, and it was already identified in the early 60s by Edgar Dijkstra. The most commonly known example for explaining concurrency issues is the dining philosophers problem, which was also introduced by Dijkstra together with the introduction of the race condition problem and the according solution. The dining philosophers can be found in nearly all literature about concurrency and parallelism. We also linked some material for you on the webpage. And this is the fact because it actually explains very well all the relevant issues we get with concurrency and with race conditions without binding itself to any kind of hardware or software that is actually in the field. The dining philosophers work in a way that you have a thought experiment, and in this thought experiment we assume that we have 5 philosophers that are normal humans, so they get hungry from time to time despite doing their work and thinking about the world problems. And when the philosophers want to eat, they use there's a separate eating room, and in this eating room they have a circular table which is surrounded by 5 labeled chairs. On this table you also have 5 forks, and in the middle you have a large bowl of spaghetti which is constantly replenished. So the situation we have here is that all philosophers, or each of the philosophers, needs 2 forks for eating, but we actually don't have enough forks to make it possible that all of them get such resources at the same time. So the situation we model here is that when a philosopher gets hungry, he comes to the eating room, he sits down on his chair, he first picks the left fork, then he picks the right fork, then he starts to eat because he has all the tools he needs in order to access the shared resource, which is the food. And then when he's done, he puts down both forks at the same time, and then he leaves until he gets hungry again. If we have the situation that somebody picks up a fork, but he doesn't get the other fork, then he will actually wait until he gets the second fork before he starts to eat. The thought experiment, or the model here, lies in the fact that we have concurrent activities modeled by the philosophers, and we have shared resources, which are the forks. And we have the situation that the access to these shared resources somehow must be synchronized. So we deal with classical concurrency issues, and the question, can we have any kind of race conditions in the situation where in a particular interleaving of the philosopher activities, we get problems with the access to the shared resources. And the classical examples for the dining philosophers problems, or the crucial concurrency issues we can identify here, are the following ones. The first one is that we have a situation of so-called mutual exclusion. Mutual exclusion means that no 2 neighbors can eat at the same time because they both need 2 forks, and the fork in the middle between the 2 chairs is actually a shared resource. So whatever kind of interleaving we have, when 2 neighbors on the table want to eat at the same time, we run into a synchronization problem. Due to the eating policy, we may have the situation that some of them never get their turn. And this is a problem we call starvation. So in a concurrent system where some of the activities due to scheduling, due to other policies, never actually get a chance to run on the processing elements, we have a starvation problem, which is typically bad, because if some of the concurrent activities have no chance to finish, then normally the overall application has no chance to finish. Starvation is therefore one important problem that can be found in concurrent programming. Another one is the so-called deadlock. This is also widely known in software and hardware industry as a problem. And if you put that down to the philosopher thought experiment, it can be modeled in a way that you assume the situation where all philosophers start to pick up their left fork at the same time. This would work because we have 5 chairs and 5 forks, but the problem is if everybody has a left fork in their hand, they are no longer able to take the right fork. And since we made the policy that the philosophers wait for the right fork until they start to eat, there will be no more progress. The system is stuck, nothing can happen anymore, and this is what we know as deadlock. In IT systems, deadlocks are commonly visible by having systems that no longer react on any kind of external input. This is a bad thing, so actually one of the obvious ideas would be now to change the policy a little bit and to allow the philosophers to lay down the second fork again when they see that the right fork is not available. This would prevent the deadlock in the system, but it brings us another problem, which is the so-called lifelock. Lifelock is a problem where you have local progress, so some of your concurrent activities are able to progress, but the overall application is not able to get forward. An example you find in literature often is 2 people facing each other on a very narrow flow and jumping in front of each other in order to try to get beyond the other. This is a lifelock situation, and it can also happen in concurrent systems, even when you thought you solved, for example, a deadlock problem by the mechanism that now actually gives you the lifelock condition. So in general terms, when we go away again from this thought experiment, we have as first concurrency issue the mutual exclusion. So we have the requirement that one concurrent task should be able to exclusively use a shared resource so that no other is able to use this resource at the same time. This is the implementation of the fork grabbing mechanism. We need mechanisms to ensure that in concurrent systems, for example, in order to ensure correctness of the program. The second thing we have in concurrent programming is deadlocks as a possibility, where none of the tasks is able to proceed anymore. Starvation is a problem where a running task, a task that would be able to do some concurrent work, is overlooked indefinitely, so it has no chance to actually use the processing element, to use the resource, and this leads to the fact that the overall application, the concurrent application, cannot finish. And the last important concurrency issues we know is lifelock, where 2 or more concurrent tasks continuously change their state, so they're not deadlocked in their own local situation. They think they have progress, they can work all the time, but the overall application cannot progress. So there is no global forthcoming in what the application is intended to do. When we take these different concurrency issues and now look on what can happen in reality, we basically distinguish between 3 different classes of concurrency. And in all these classes, the described concurrency issues can occur. The first class are independent tasks, which have no awareness of each other. An example here would be different applications, different processes running in an operating system, like Word and a web browser. So these applications know nothing from each other. They basically run concurrently based on the operating system scheduler mechanisms, but they do not share resources. If they do not share resources, we don't have the described problems here in first term, because there is no fight or interleaving issue regarding shared state. So the task results from these different concurrent activities are completely independent of what happens elsewhere in the system. Concurrency problems that may occur even though are the ones that happen due to the sharing of hardware resources. So if the operating system is offering resources to these 2 applications, for example, reading input data from external devices, there might be internal concurrency challenges and fights when the operating system primitives are running, but this happens on the lower levels and not on the application level. The second example, or the second class of concurrent applications, are the ones where you have dependent tasks. So you have different concurrent activities defined in one application, and they're sharing resources, for example, variables, memory, operating system handles. And they do this in a collaborative fashion. So they know each other, they know that they try to achieve some better performance, for example, throughput, as with the server example, by sharing the computational resource. And this needs mutual exclusion mechanisms. So you must somehow make sure that no race conditions can occur by protecting your shared resources. And if you don't do that in the right way, you may come into the situation that the task results depend on the other's behavior, which is a bad thing. So we want to avoid that race conditions. The third class of concurrency in applications would be then dependent tasks sharing a communication channel. So this boils down to what we have learned to know last week as shared nothing systems. And this is a similar situation to what we have in shared memory systems. So here the sharing is not about variables or memory in the same machine, but here the sharing is about the communication channel. So messages float forward and backward between the concurrent activities, and somehow we must make sure that our local behavior and the overall application result does not depend on the interleaving of the activities on the different concurrent processing elements.